You wouldn't burn. You'd never get the chance. That's the first thing I want to knock out of your head, because it's the assumption everybody makes instantly. Falling into the sun. Some slow, dramatic roast. Skin blistering. You feeling it happen step by step like a marshmallow held too close to a campfire. Forget that image completely. You'd be gone, fully, structurally gone, long before your body had any opportunity to register heat the way you're imagining it. The real story isn't about burning. It's about how many different ways the sun can erase something, and the order in which it does it. And that order is stranger than any burning scene you've got in your head. Let's fix the first wrong assumption, because it's the one holding everything else up. We think of the sun as a really hot fire. Bigger flame, same idea, just turned up. It's not. Fire, actual fire, the kind on Earth, is a chemical reaction, oxygen combining with fuel, releasing energy through chemical bonds breaking and reforming. That's not remotely what's happening inside the sun. The sun is gravity, crushing hydrogen atoms together so violently that their nuclei fuse, actual atomic nuclei merging into heavier elements. And that fusion releases energy on a scale ordinary combustion can't even approach. Calling the sun fire is like calling a nuclear reactor a candle because they're both bright. Same word, completely different physics, completely different scale of violence. So here's the honest order of events, because it matters. You don't hit the visible surface first. Long before that, you'd pass through the corona, the sun's outer atmosphere. And here's the part that trips people up. The corona is hotter than the surface underneath it. Way hotter, over 1,000,000 degrees, even though it's far less dense than the layer beneath. Nobody has a fully agreed upon answer for exactly why the corona runs hotter than the surface it surrounds. That's actually one of the real unsolved puzzles in solar physics, sitting right there in plain sight. But regardless of the why, the effect on you would be immediate. Radiation of that intensity would tear apart molecular bonds in your body almost instantly. You wouldn't feel pain building up in any way you'd recognize because the nerve signals themselves, the actual electrochemical process your body uses to register "this hurts," would stop functioning before that signal could complete its circuit to your brain. Pain needs time to travel. You wouldn't have any left to give it. And gravity isn't waiting politely for radiation to finish its job either. It's doing its own separate work on you at the same time. The sun's gravity is about 28 times Earth's. Falling toward it, you'd accelerate to genuinely enormous speeds, hundreds of kilometers per second by the time you're getting close. And because gravity's pull gets stronger the closer you are to something, the part of your body closer to the sun would get yanked harder than the part farther away. Your feet, say, pulled more violently than your head, stretching you unevenly along your length. That's called a tidal force, the same basic mechanism that raises tides in Earth's oceans, except here it's strong enough to physically pull a body apart, independent of any heat at all. So even setting radiation completely aside, gravity alone is enough to end things mechanically. Now here's a paradox that should genuinely make you pause for a second. The sun isn't a solid ball you'd hit the way you'd hit a wall. It's plasma, gas so hot that electrons get stripped clean off their atoms, and there's no hard surface anywhere in there. You wouldn't crash into anything. You just keep sinking deeper and deeper into progressively thicker, progressively hotter plasma. And yet, here's the thing. None of that emptiness saves you. It doesn't work out as some gentle drift into nothingness. Density increases fast, temperature climbs violently, and no solid surface doesn't mean no destruction. It just means the destruction unfolds in stages, layer by layer, instead of happening all at once in a single dramatic impact. By the time you're inside the corona, something genuinely strange is already happening to what you even means. The atoms making up your body are getting stripped of their electrons, becoming plasma themselves, physically becoming the same kind of material the sun itself is made of. There's no clean, sudden moment where you stop and sun begins. It's not a line, it's a gradient, a smooth transition from organized thinking person into indistinguishable solar plasma. And somewhere in that gradient, the concept of you simply stops applying, without there ever being one identifiable instant where it happened. Here's where it gets genuinely beautiful to me, though, and I don't use that word lightly in a video about being destroyed by a star. The atoms that made up your body don't just vanish. Matter doesn't work that way. Energy and mass are conserved, always. Those atoms become part of the sun's plasma, get caught up in convection currents inside it, and here's the wild part. Some of them could, in principle, take an almost absurdly long path back out. Photons of light generated deep in the sun's core take somewhere on the order of thousands of years through a slow, chaotic process of being absorbed and re-emitted over and over, sometimes called a random walk, just to work their way from the core out to the visible surface. So in a strange, real, literal sense, energy connected to atoms that were once you could eventually leave the sun as sunlight, traveling outward, hitting some distant planet maybe, thousands of years from now. That's not poetry. That's just what conservation of energy actually allows for. I want to be straight with you about where our precision runs out, though, because I don't like pretending we've got a clean, exact answer when we don't. We don't have a precise, verified model for exactly how a human body would disintegrate, millisecond by millisecond, inside solar plasma, because obviously nobody's run that experiment. And simulating it accurately means dealing with physics at extremes we almost never need to calculate for anything else humans actually do. We know the broad order of destruction with real confidence: radiation damage first, then gradual integration into the plasma itself. But the fine-grained timeline, the exact sequence of what breaks down first and how fast, that's extrapolation from known physics, not something anyone's directly observed. I think it's important to say that plainly instead of presenting a fake level of certainty just because the broad strokes sound confident. Now let's widen this out, because I think there's something bigger sitting underneath all of it. Every atom in your body, heavier than hydrogen and helium, carbon, oxygen, calcium, iron, all of it was forged inside a star that lived and died long before the sun even existed. You are, right now, sitting there made of stellar material, atoms cooked in the nuclear furnace of some ancient star, scattered across space when that star ended, and eventually gathered up into the dust cloud that became Earth, and eventually into you. Falling into the sun wouldn't be leaving that cycle, it would be rejoining it. Atoms that came from starlight, briefly organized into something that could think and fall and wonder about falling, returning to become starlight again. So I don't want to close this with something reassuring, because I don't think reassurance is honest here. But I do want to close with something true. The boundary you feel between yourself and the sun, the sense that you're one thing and it's a completely separate other thing, burning 93 million miles away, that boundary was always thinner than it feels. Same atoms, same physics, same fusion-forged material on both sides, just arranged for a while into something capable of asking the question in the first place. The sun's not doing anything special to you if you fell into it. It's just doing what it's always done to matter, organizing it, then reorganizing it again, and you'd simply be the latest small, brief arrangement to pass through.